Hi, welcome to what might be the first of many YouTube videos about meteorites. Depends on what the reaction to this one is. This being possibly the first of a series, I thought I'd start off with a look at the origin of meteorites, where they came from, and particularly linking them to planetary bodies throughout the solar system and what we've learned by doing so. Okay. I suppose some of you probably do know about meteorites already, or we wouldn't be watching this. But if you don't mind, at the risk of being accused of teaching my gran how to suck eggs, I'll assume that not everybody has the same level of knowledge, and I apologise if I'm telling you things you already know. But generally speaking, there are four types of meteorite that we regularly encounter. The oldest and most abundant are the chondrites, and they accreted from the solar nebula. That's the cloud of dust and gas from which condense the sun and the planets at the start of the solar system. The very oldest ones are called unequilibrated meteorites, and as you can see, they contain little tiny spherical objects called chondrules, and these condense directly from the solar nebula, a mechanism that's not completely understood yet, but it's a sign of a really ancient meteorite over 4.5 billion years old. So at the start of the solar system, there are bigger and bigger chunks of this stuff accreting and bashing into each other to form eventually small planets, planetesimals. And those, when it reached a large enough size, sort of gravity inside them tended to cause the heavier elements, the metals, to sink through to the center to form a core, like the Earth's nickel iron core. And it's assumed that iron meteorites, which are probably the second most abundant, represent the cores of planets that were liberated during massive collisions. They're roughly all the same age, 4.2 billion years ago. So it's assumed there's a lot of bashing on collisions going on at that time. If you've got a differentiated planet with an iron core, around it you'll have a mantle, like the Earth's mantle, and like the Earth, that was mostly composed of the mineral olivine. That's actually the gemstone peridot, as a matter of fact. And here you can see what's called a stony iron. This particular stony iron is called a palisite, this type, and it, as you can see, it has a metallic nickel iron matrix from the core. Suspended in it are crystals from the mantle. The crystals, and therefore it's assumed these represent meteorites that were generated from the core mantle boundary of a planet that broke up. The last group, the achondrites, well, they're called that. The prefix A means without. Achondrites don't have any chondrules, don't have any of these, and they're known to be from the surface of fully differentiated bodies. They're depleted of heavy metals, and they don't have any chondrules, and they have the structure and chemistry of material from the surface of a planet. Quite excitingly, some achondrite meteorites have been demonstrated to be from the Moon, Mars, and in the case of these recent rocks, meteorites, possibly even Mercury. If we look at the lunar achondrites, first of all, where, again, I'm simplifying this, there are more types of lunar meteorites, but broadly, you have anorthosites, which are mostly made up of feldspar, and tend to have come from the montane regions of the Moon, mountainous regions. Either on this side, I mean, there are mountain chains all over the surface of the Moon that we can see from Earth, the Apennines, the Alps, and so on and so forth. But there are a lot more. It's a lot more highland areas on the other side of the Moon, and interesting. It's assumed that most anorthosites, or many of the anorthosites, will have come from the far side of the Moon. The side we can see with a small telescope or binoculars, or even a naked eye, you'll notice it's basically quite pale. The Moon has a high albedo, it reflects a lot of the light it receives from the sun. But there are also dark areas, which, if you look at them closely, you'll realise that they're circular. And what they are they're referred to as the seas, or the Maria on the moon. And we all heard of the Sea of Tranquility. Then you have the Ocean of Storms, the Bay of Rainbows, and so on. In the past, astronomers actually believed there were bodies of water, but we now know they're flood basalts, where enormous impact craters were made, by cometry or asteroidal impacts on the surface, and that basaltic material welled up from underneath to fill them up, creating originally smooth, dark plains. Of course, subsequent impacts, thousands, millions of impacts over the time, has pockmarked the surface of these. If you see the images from any of the Ranger or Surveyor or Apollo missions, you'll know that the Maria basins are actually now covered with craters down to centimetric size. Some of these basalts obviously were, as it's filled up by volcanic, because the moon was seismically active at the time they were formed. So some meteorites from the moon, therefore, are basaltic, and some are feldspathic and other sort. Breccias just mean, or breccias, whichever you want to pronounce it, just means something that's made up of fragments of other material. The regolith of the moon is its surface impact melt. Breccias obviously is where there's been a massive impact. It shattered the local rock and then immediately welded it back together, and so on and so forth. The situation's slightly different with Martian meteorites. Again, there are recent additions to this, but they're traditionally were called SNC meteorites after Shergottites, Nakhlites, and Shassinites. The scarcest of these are probably Shassinites. There's only 2 of them known, and they're named after the type meteorite, the first one discovered, which came from Chassigny in France, and they are what known as dunites, or mantle material. So, in other words, they come from deep down beneath the surface of Mars, and probably therefore from a single, possibly a single large impact. As I say, there are only two of these known. And olivine, remember, is what we associate with the mantle of a planet. Shergottites, again, these may well have come from a single crater, because they're all the same age, roughly 130 million years old. And they're crustal, in other words, from the surface of Mars, okay, or just below the surface of Mars. And the last group, the Nakhlites, interesting story about that. Shergotti, by the way, is in India. Nakhla is in Egypt, and Nakhlites, interestingly enough, the fall they're named after, the Nakhla impact, is actually, the meteorite actually struck a dog, allegedly, and killed it. It's a bit unfortunate for the dog. But what's amusing is the fact there's an American meteorite dealer who calls his website Nakhla Dog Meteorites, and he has his logo is a Basenji dog with a crater in the top of his head. So it's slightly off the wall humour, as it were. But they're basaltic. Now, the interesting thing is, like the moon, Mars will have had basalt floodplains and so on and so forth, formed not just by impacts and upwelling following impact, but also Mars has got incredible volcanoes. I don't know if it's still the case, but it's always said that the largest volcano in the solar system is Mons Olympus on Mars. It's gigantic, shield volcano. And an eruption, Mars is not, although it probably is seismically active to some extent, in that I believe outgassing has been detected and so on and so forth, but there are no huge, massive volcanic eruptions occurring now, but there were billions of years ago, and some of those must have been energetic enough to chuck plutonic rocks from below the surface of Mars, like lava bombs and stuff like that. Must have been, the eruptions must have been able to chuck these things out into space, because Mars, being smaller than, much smaller than the Earth, has got a much lower escape velocity. So it's possible that some Martian basalts were sent into space from volcanic eruptions. Good friend of mine in Germany, a chap called Stefan Rallo, he's a bit of a planetary specialist, and he's there's nothing he doesn't know about planetary meteorites. And he obtained in Morocco a few years back a stone. Meteorites are named after the place where they're discovered. NWA stands for Northwest Africa. 7325 means it was the 7,325th stone found in that region of North Africa. He actually obtained it in Mercury, in Morocco from one of the local collectors, and instantly recognised that it was a diogenite, which is from below the surface of the planet. And once it had been chemically, I knew it was something unusual. It was quite different looking. I have my own piece here, and lucky enough to have had several others over the years recently. But when it was chemically analysed, it was discovered that it had chemistry very similar to what was anticipated for meteorites from the surface of Mercury. By process of spalling, if a large object smashed into Mercury, particularly if it was the side facing away from the sun, the material could be ejected outwards. The energy of that impact would eject material outwards. And it, again, because Mercury is fairly small, it has been calculated that it's possible that spalled material from Mercury would travel outwards to the outer solar system, where we are. Or if you like, the outer reaches of the inner solar system. There's another meteorite too, which is a very scarce type of meteorite called an angrite. And again, from time to time, I've had samples of this. It's called NWA 2999. And it's another one that has many of the chemical characteristics we'd associate with material from Mercury. So kind of watch this space. But this one it's got a lot of serious support that it is mercurial. But most achondrites are known to have come from not the major planets, but from various asteroids. I guess people generally, if you ask them what the asteroids are, they'll say they're lumps of rock that orbit in between Mars and Jupiter, and that's to some extent true. What's called the main belt, where the major part of the bulk of the asteroids in the solar system are found, does in fact exist between them. And it used to be considered either it was a planet that had been broken up by the gravitational pull of tidal pools of Jupiter and Mars, or it's a region, a null region in the solar system where a planet couldn't, where the process of accretion couldn't take place. Generally speaking, that's not considered to be the case now. It's considered to be it is a null area, but it's an area of the solar system where material has migrated outwards from the inner solar system and inwards from the outer solar systems. We'll see in a minute. But they're not the only asteroids. There are asteroids actually within the orbit of Jupiter, and there are asteroids within the orbit of Mars. In fact, as you can see, the Amors, Athens, Apollos, all of those in theory could cross the Earth's orbit. And people spend a lot of time worrying about a collision with a large asteroid. One thing I would say, if your mental image of the asteroid belt is based on things like Red Dwarf or Star Wars or Star Trek or anything like that, it's not a very accurate representation. For a start, although there are lots of asteroids, most of them are quite small. And the total mass, if you add it all up of all the asteroids in the solar system, comes to much less than the mass of the Moon or Titan, the largest satellite of Saturn. And they're quite far apart. It is a fact, if you stood on any asteroid anywhere in the asteroid belt, you wouldn't be able to see another one. Okay, they are separated by considerable distances. You wouldn't have to swerve in and out among them like the cat does when he drives the bug on Red Dwarf. Okay. Now they're classified. These are the four major groups of asteroids that we're aware of. Incidentally, the asteroids tend to be named according to or are named in order of when they were first discovered. And Ceres was the first to be discovered. So astronomers generally refer to it as one Ceres and so on. Vesta was the fourth to be discovered, generally referred to as 4 Vesta. Okay, well, the most abundant of all the asteroids are the carbonaceous asteroids, which are greyish in colour. Ceres, the largest, for example. and they consist of clay and silicate minerals. And they orbit in the outer regions of the main belt. And as you'll see, there's a good reason for that. In the inner main belt, you have the S-type silicaceous asteroids, which generally, as it says, you can all read, greenish or reddish, they make up about 7%. And they consist of silicates and nickel iron. Now, they do have a nickel iron component, usually in the form of a core, if they're large enough. Then you have the M-type asteroids, and they are literally just lumps of metal. And it's considered they're probably certainly the cause of disrupted larger asteroids. And lastly, the V-type, or anomalous asteroids, which include Vesta, that's why they're V-type, and they have basaltic crust. In other words, in many ways, they're like a miniature planet, a proper miniature planet with a full differentiation. So therefore, for all these reasons, it's likely the C-type asteroids, they migrated inwards from the outer solar system after the formation of Jupiter and Saturn, while the silicaceous ones did it in the opposite direction. After the formation of the inner solar system, they moved outwards. And the M-type, as I said before, are the cause of shattered S-type asteroids. Now, again, I don't want to sound patronizing here, but we need a little bit of chemistry to understand how we can work this out. I mean, how do we know that lunar meteorites come from the moon, or HEDs come from Vesta? Okay, I suppose all of us know that, or remember from school, that the universe is made up of just over 100, 115, 120 different what are known as elements, and the elements are different, represent different types of atom. So the universe is made of atoms, the basic building blocks. I'm sure we all remember. The smallest, the most simple, is the atom of hydrogen, which in its simplest form consists of a nucleus containing a single proton, a positively charged particle, and it's convenient to think of them being in orbit, but they're not really. They exist in space in various areas of probability. Small charged particles called electrons, much smaller, called electrons with a negative charge, and it's the electrostatic charge between the negative electron and the positive proton that keep them in their positions. And we're not going to get into quantum theory, how they can actually jump up and down from one level, energy level, to the next, and so on and so forth. But atoms can also have a third particle, okay? Even hydrogen can have a third particle, and it's found in the nucleus. I mean, in fact, as probably we all know, if we watch Brian Cox on the telly, there are dozens, if not hundreds, of subatomic particles, much smaller particles, components, with highly exotic names and properties. But the three main ones, the third one is called a neutron, and it's about the same size as a proton, but it has no electrostatic charge. It's neutrally charged, and again, it's found in the nucleus. Now, whereas the great majority of hydrogen atoms just have a single proton in the nucleus and no neutron, you can also get a variety called an isotope, as it's called, of hydrogen called deuterium, which has two particles in the nucleus, a proton and a neutron. I should say that the number of protons or electrons, come to that because it's always the same, that any element has is called its atomic number. So whatever the isotope of an element, it always has the same atomic number. In the case of hydrogen, of course, it's 1. But of course, what can vary is what's called its atomic mass. So deuterium has an atomic mass of 2 because it's got 2 particles in the nucleus. Tritium has got an atomic mass of 3. It has 3 particles. That's a proton and two neutrons. Don't forget the number of protons has to stay the same. And that's true of every element in the periodic table. They can have whatever their atomic number, which always remains the same, their atomic mass varies depending on how many neutrons there are. Now, that comes of interest to us meteoriticists when we look at oxygen. Oxygen has a number of different isotopes on Earth by relative amounts. The most common by far is oxygen-16, which has got 8 protons, 8 neutrons, okay? Therefore, its atomic number is 16. But you also get oxygen 17 has 9 neutrons, and oxygen 18, which has 10. And you can see they're far less abundant. But that relative abundance is characteristic of all oxygen on Earth. So whatever rock you find it in, whether you find it in water, whether you find it in a metal oxide, wherever you find it, the isotopes of oxygen are found in those relative abundances. And it turns out that if you plot those abundances on a graph, I'm not going to go into technical details of this, but you can see that it's basically comparing the percentage in any sample of oxygen 18 with oxygen 17, the 2 rare isotopes in that previous chart. You can draw a line, okay, a graph, a line. And any Earth rock will lie on this line somewhere. And it turns out that's also true of rocks from the moon, whether they're meteorites or rocks brought back by landings on the moon. And it turns out that meteorites, which were suspected for various reasons and being from Mars, they lie on another relative oxygen isotope line here. And the same is also true of meteorites which were considered to be from Vesta, the HED group. They lie on this relative oxygen isotope distribution line. Now, you know, this has led to some fascinating discoveries. For example, there's a rare type of meteorite called a brachyonite, and several of these, including this one here, and NWA, remember Northwest Africa, 6077, plots on the terrestrial fractionation line. So how did a meteorite leave Earth and end up in space? For, I would assume that would be before the Earth had a dense atmosphere. So billions of years ago, before the Earth built up a dense atmosphere, a massive impact, could even be the impact that created the Earth-Moon system, blasted this material off into space. It's traveled around the solar system and come back again, but it plots on the terrestrial fractionation line. Of course, that suspecting that HEDs are from Vesta and finally they all plot on the same line isn't, in a sense, it's not cut and dry conclusive, is it? And so we enter the world of spectroscopy. Most people at some point will have seen it done that you pass white light, a beam of white light through a glass prism, as it's called, a specially shaped piece of glass. And that will, I think it was Isaac Newton famously who first formulated this, and that will split it up into the various wavelengths of light, the so-called spectrum. So you have the red, orange, yellow, green, blue, indigo, violet, and beyond that you have the ultraviolet, inside that the infrared. And you can use this principle to split the light, reaching Earth from a planet or a star system. Obviously, it's from a planet. It's light that's been reflected off the planet's surface by sunlight that's been reflected by the planet off the planet's surface. Generally speaking, you wouldn't use a prism in a spectroscope. It's a graticule, very clever piece of like a grating. Again, I shan't go into technology, but it's just much lighter and it's much more successful way of doing it. I was very lucky to be associated with after I finished teaching, to be invited to do some work in a school in West Norfolk by an incredibly gifted and talented teacher, fantastic head of science at the school. And he ran an astronomy group, a wonderful astronomy group. And they did some really clever experiments using my meteorites at some point. And what they wanted to do was compare, first of all, they took the reflected spectrum of the asteroid Vesta. I mean, at the time of writing, at the time of this broadcast, if you go out at night and look up and see the constellation Leo, which is, not far off overhead at 10 o'clock at night at the moment, you can, with a pair of binoculars, you can easily find Vesta, the asteroid. It's about magnitude 7, so binoculars and telescope will easily find it. It's even easier if you use a camera, okay, a mounted camera. Okay, So that's the principle, using a telescope with a spectroscope attached to it. This teacher and his students took the spectrum of Vesta. I should just point out, I mean, again, I don't want to teach going out to suck eggs, but we tend to forget our high school science as we get older. Things are the colour they are because of what they reflect. For example, a plant is green because it's absorbing the red end of the spectrum, absorbing all this, and reflecting the green end, which lets you into the basic principle that a plant photosynthesizes using sunlight. It doesn't use all the sunlight, it uses the red end of the spectrum of light it receives from the sun. It uses that for photosynthesis, and this it just reflects, throws it away, if you like. So when you see a blue shirt, it's blue because it's reflecting the blue light and absorbing all the others. When you see a black surface like this, it's black because it's absorbing all the wavelengths of light that fall on it and reflecting nothing. So when you look at Vesta, this reflectance that varies from hardly anything down the violet end up to great majority is reflected up the red end. It tells you that minerals in the regolith of Vesta are absorbing wavelengths at a different rate. And it turns out that's quite characteristic. Now, what's fascinating, that using a chunk I had of the Tatooine diogenite, you can do a reflective spectrum by shining pure white light on it, and again, passing it through a spectroscope, and you'll see that it exactly matches it. The shape is exactly the same. The same things are absorbed at the same rate. And it turns out that if you continue that process and try it out on different asteroids, and you can link them to various groups of meteorites. For example, 44 Nysa has the same relative reflectance spectrum as Enstatites. 4 Vesta, as well as Diogenites, has got the same reflective spectrum as basaltic achondrites. Okay. And so it goes under the Eros, Psyche, of course, is a metal one, and Ceres, you know. So Ceres has got the same reflective spectrum as carbonaceous chondrites, which is why, you know, as I say, Ceres is classified as the type meteorite in the C group of asteroid, type asteroid in the C group. And if you look at Vesta, it has this enormous crater here, huge impact crater, and it's assumed that was the source, that impact that made that was the source of the HED meteorites. Here they are. HED stands for Howardites, Eucrites, Diogenites. Diogenites are material like that Tatooine one in the previous slide. They're material excavated from deep down under the crust, from the mantle of the planet, and they're mostly made of olivine, this little greenish colour. Eucrites are from the surface, from the regolith of Vesta, and Howardites, as you would anticipate, you will get meteorites which are composed of a mixture of the two that fuse together during the impact. So you've got diagenetic material and eucritic material fused together by the impact to form Howardites. So the HED group are the ones that come from Vesta. Of course, you can get diogenites and eucrites, etc., from any other asteroid. In fact, here we are. Other asteroids seem to have been the source of different types of meteorite, which really perhaps not that surprising. Psyche, an intriguing great big lump of nickel iron floating about there in space, is thought to be, you know, typical of an M-type asteroid, the core of a disrupted planet. But both the Japanese and the Americans, NASA Space Agency, are planning close visits to Psyche. When you look at a plutocrat like Elon Musk, he's not building spacecraft for fun, although I suppose there might be an element of that. There is money to be made out there. I mean, even a smallish asteroid like Psyche, it's got more nickel iron and all the other metallic elements in the periodic table, you know, than we can easily access from the crust of the Earth. All our mining and excavations on Earth all come from the crust. It's not like we can burrow down and extract iron from the core of the Earth. So at some time in the future, the theory would be you could harness, you could capture an asteroid and drag it back into an orbit close to the moon or the Earth, and you could actually use it as a source of raw materials. Watch this space. You'd be surprised what is being planned in the future of space exploration or space exploitation, to be more honest. These here are the various iron type meteorites that are thought to come from N type, and they're really intriguing. Down here we have a cross section through that particular one is a meteorite called Campo del Cielo, and it shows what's known as the Whitman-Staton pattern. The impact that liberated us from the core of a planet must have been incredibly energetic and create immense amounts of heat, which took a long time to radiate out into space. Because don't forget, you can only get radiation. You can't get conduction in space or convection. And it must have taken thousands of hours, if not years, for this thing to cool down. Because if you've ever grown crystals of copper sulfate or sugar when you're a kid at school, you'll know that the longer you leave them, the longer time you allow them to grow, the bigger they get. As you just, evaporate the solution, you just get tiny little crystals like sugar. So the size of the crystals, I've got individual crystals from this particular meteorite, Campo del Cielo, with a mass of 300 grams. So, and I'm sure bigger ones exist. And what you're looking at here is the two major minerals, teenite and camosite, that make up nickel iron meteorites. Here's another one. This is a meteorite called Semshan, and you can see though similar, this pattern of crystals, the Whitman-Staton pattern, which you achieve by polishing it and etching it. They have slightly different solubilities, those two minerals, and so you get you can actually see the Whitman-Staton very plainly on there. You'll notice they're different, and that's in fact how iron meteorites are classified according to the size of their Whitman-Staton pattern. This is a typical big lump. In fact, this is Campo del Cielo. I suppose almost everybody's favourite are the ones I mentioned before, pallasites. Pallasites being nickel iron matrix with a, as you can see, with olivine crystals. This is a Russian one from a place called Semshan. I mean, I suppose I could possibly get the light to shine through it so you could see. If you can see that, it's actually has translucent crystals. And they're beautiful meteorites, pallasites. And they're from the core mantle boundary of the disrupted planet. One here. Okay, I mean, some meteorites that landed on Earth a long time ago. This is particularly from this particular one is from a Chinese meteorite called Nantan. It was so abundant that for a long time it was used as a source of metal. Okay, and asteroidal collisions are thought to be the source of most chondrites. Remember chondrites, the ones that have chondrules in them? Well, if they're from a large asteroid, they wouldn't have chondrules, but they'd still be chondritic material. They'd still be a chondrite. And these are the four, I mean, again, there are much more than this, but these are the four main groups. So ordinary chondrites. I mean, the oldest material in the solar system are the ordinary chondrites, and the very, very primitive ones, the ones showing the chondrules in them. If you remember right at the start, chondrules, the ordinary chondrites are 4.5 billion years old. And if you can see this one here, when you cut and polish them, you can see chondrules. There's a chondrule there and another one there. But I get a light on it. You can also see, I hope, that there's kind of metal sparkling in there. And that's how they're classified, by the presence or absence of chondrules, and by you see the metal just sparkling there? There, got it. You can see little metal particles sparkling in the polished section. So chondrites are classified according to the amount of metal they have in them. The more they have, if they've got lots of metal, they're called H chondrites. Okay, if they haven't got much metal, they're called L for low chondrites, and everything in between. The chondrules, as you remember, during the process of equilibration, the chondrules will disappear through chemical action and heat, you know, and pressure. And so only the most primitive ancient chondrites actually show the chondrules. I think, well, I haven't got one of those here handy. Anyway, if a meteorite does show chondrules and they're abundant and they're obvious and they're large, that's given a low number. In fact, the lowest number ever given, ever assigned to chondrites is 3. So if you had if you had a meteorite with not much iron in it, or metal, in other words, and with large obvious chondrules, it would be called an L3. If it had lots of metal and no chondrites, no chondrules, it would be called an H5 or 6. Okay. So the higher the number, the chondrules will never be, they'll be absent, they won't be visible. So that was a bit long and tedious, wasn't it? Still, you can see chondrules here quite plainly in this carbonaceous meteorite. Carbonaceous meteorites are obviously thought to come from C-type asteroids. For this to have such obvious chondrules, it must have been a very, very small one. In fact, it's more likely that this particular carbonaceous meteorite would be called a CV3, 3 because it's got large, obvious chondrules. It's probably one that condensed in the original solar nebula. And the reason for thinking that, apart from the fact it's got these obvious chondrules, which would have disappeared during planet formation, aside from all that, these are really exotic. CV3s have been, several of them been shown to have this dark matrix, this sooty carbonaceous matrix, contains a kind of soup of exotic macromolecules, amino acids particularly. Now in you, and in all life on Earth, there's only 20 odd amino acids, okay? But some of these CV3s have been shown to have over 100, and people often look to them as being a possible contributor to what's called panspermia, the transport of life or large macromolecules around the universe. Fred Hoyle was a great, Wickram, a singer, were great believers in that, the two astronomers. The Enstatite group is made up of magnesium silicates, Enstatite, and there are plenty of other so-called rare or scarcer ones like rumarutites and stuff like that. Oh, I should have shown you, I didn't, that's a lunar meteorite, a small slice. I mean, I have much bigger ones than that occasionally, but that's a recent discovery, a thing called tessellitine, and it's a breccia, you can probably see, but okay. So the E-type, the Enstatites, they contain high amounts of this mineral magnesium silicate, and 3 asteroids have the right relative reflectance spectrum to suggest that they might be the origin of the Enstatites, these nicer Angelina Hungaria. Lastly, but not least, well, yeah, least really, unusual little things called carbonados. They, the typical examples you come across are about 2 or 3 grams, 2 or 3 millimeters across. Okay, they're quite small, and huge quantities are mined in Brazil and in Central African Republic. And of course, the vast majority, being small, are used for industrial purposes. You can buy them from diamond dealers, but they're not associated with the normal diamond volcanic pipes and so on and so forth, and kimberlite, where you normally find diamonds. They exist in just large strewn fields in these 2 areas. Bear in mind, before the Atlantic Ocean basin spread open from the centre, because of plate tectonics, the movement of the 2 plates in opposite directions, the 2 strewn fields were actually united as one. Now these are from Brazil. You can't actually, you're not allowed to have them, I don't think, any longer from Central African Republic, because they're classified as conflict diamonds. Well, I've had these up to the size of a big grape or a small plum. So they can get quite large, and they can be polished, they can be turned into gemstones at that size. What's interesting about them is they contain high amounts of hydrogen, which has led many astronomers and meteoriticists to suggest a very exotic origin for them. I guess most people know that the gas giant Uranus, or Uranus, however you want to say it, is tipped over in its orbit, tipped over its axis is tipped at 97 degrees. So the planet kind of rolls around the sun in its orbit, okay? And you know, there have been various attempts to explain why that happened, why the axial tilt is so dramatic. I mean, the Earth's got an axial tilt of 23 degrees, as you probably know, which is what accounts for the seasons on Earth. They don't have seasons in the same way on Uranus because it's as you can see, there's the gas clouds showing that, you know, the equator's kind of here. So that's a pole. So the same pole is always pointing towards the sun. So what's responsible for that tilt? It has been suggested that a massive object, perhaps a huge comet or a Kuiper belt object from the region outside the very limits of the solar system, might have smashed into Uranus at some point and literally knocked it over. And that the tremendous pressure and compression produced during that collision was sufficient to compress the molecules of methane, which make up most of the outer atmosphere of these gas giants. Methane is CH4, carbon and 4 atoms of hydrogen. You know, that compression has been shown in laboratories to be able to turn methane into diamond. You can do it with coal as well, coke. So that's a possibility. Yeah, I think more and more people tend to think that there's another possibility about carbonados, which is that diamond has been shown to be quite common in interstellar space. And it's the end product of some solar, stellar evolution is just a huge chunk of diamond. Okay. So just to sum up then, this is just a little table that shows the meteorites and the planets that many of them are linked to. So here we have the SNCs linked to Mars. Fascinatingly, a fairly recent discovery, a meteorite called Chiron, has been shown to have the same relative reflectance spectrum as Phobos, which again shouldn't be surprising, as Phobos does show signs of massive impacts. And of course, you know, it's a small body, so comparatively near to the Earth. So it's definitely a possibility. As we said before, Angrites and Diogenites, NDA 2999 and 7325, among others, have the right chemistry to be from Mercury, that Braconite from the Earth, Lunites, as we've seen, from the Moon, and then we go down to, you know, HEDs from Vesta, and Diogenites from other asteroids, and so. And then we're talking about these are meteorites with a high content of metal, and L chondrites with a low. And again, they some HL and LL chondrites do match various asteroids. Okay. Of course, it's not. I mean, that's not complete, and it's not to say that every palisite came from Asperina. Far from it. It's just that some pallasites have been linked. I know, you know, numerous pallasites have been linked to that particular asteroid. Well, I hope you've enjoyed that. And if you want to find out more about it, I mean, obviously I do sell meteorites for a living. That's why I've got all these ones kicking around here. But my website, Space Rocks UK, just type that into Google, actually does have a lot of data about meteorites and many more photographs than I've been able to show on here. So thanks for watching. I hope you enjoyed it.